Welcome to the fifth lesson on this discussion on calculus and particularly differentiation using the first principle. In this particular session, we will be discussing the derivative of trigonometric functions such as the sine x, cosine x, and tan x using the idea of the first principle. Of course, we know we will eventually know the derivatives of this function. We do not need to use the first principle all the time. But if you're an HL student, you can also be asked to show the derivative of a function or to differentiate from first principle. Show that the derivative of sine of x, for instance, is going to be cosine of x, okay? So let's start this with the derivative of the function y is sine of x. Okay, as I always tell students, so here is the question: differentiate from first principle the function y is sine of x, or if you like, f of x is sine of x. In order to do this, I tell students to always start by drawing a small diagram with a point just to help you understand what we are discussing here. Always draw this diagram here. The circular, dotted circular line there represents a point. Okay, so we are looking at the two ends of the point, A and B. And if we do that, we can choose this to be our x1 and x2 and y1 and y2, which helped us come up with the first principle. Okay, so in this case, our f of x, which should be here, is going to be sine of x, and our f of x plus delta x is sine of x plus delta x. So once we have that, we are going to need to substitute that into the principle. This is the principle behind differentiation from first principle. Okay, that is to say, our final derivative or our derived function is going to be the limit as delta x here approaches 0, meaning this is becoming a very, very tiny circle or becoming a dot of f of x plus delta x minus f of x, everything divided by delta x. In this case, our f of x plus delta x and f of x, we know them to be these two expressions there. So if we substitute that, we end up with that. All right? Now, if you've been following this, you know that as soon as we get to this stage, the next step is always to expand y2. Remember, this is our y2 minus y1 over x2 minus x1. So in order to proceed, we need to be able to expand sine of x plus delta x. But to expand sine of x plus delta x, we need to remember our compound angle formulas. All right, so our compound angle formula for sine of a plus b, I have included as well the compound angle for sine of a minus b, although we do not need it. Just for purposes of remembrance, it might help someone. Okay, so the compound angle formula for sine of a plus b is given by that. We only need the top bit of this. That is sine of a plus b is sine a cos b plus sine b cosine of a. So if we use this in the context of our variables, they are x and delta x. X is our a and delta x is our b. So if we substitute that in there and put it in the function, in our result, we end up with this. Okay, sine x cos of delta x. So that's like sine a cos b plus sine b cos a sine delta x cos x. And then we have to subtract the sine of x, which was already here. All right. So looking at that, you should notice that we have three terms in the numerator, and that the first term and the last term share sine of x. So sine of x is common to the first and the last term, so we can factorize it out and then split the expression inside the square bracket. We can split that into two fractions as such. Okay, this gives us this expression. Just take a look and see that you can understand where that comes from. Sine of x is common, so cosine of delta x and 1 there, so cosine of delta x minus 1 here after we've taken out sine, and then divide by delta x gives us that. And then we have a cosine of x and sine delta x over delta x remaining, so that we put here. We always want to keep the terms containing delta x together. So we have that there, and we have this one here, right? Okay, and what happens after that? Now we need to remember that this is a result that we already determined earlier in Unit 3 under Geometry and Trigonometry. For HL students, particularly, these results are meant for calculus, that the limit as delta x tends to 0 of cosine of delta x minus 1 over delta x is always equal to 0, while the limit as delta x tends to 0 of sine of x divided by x is always equal to 1. Okay? Right. And so the results for limit, the limit as some value of x tends to 0 of sine x over x is the same, is always equal to 1, and the limit as x tends to 0 of cosine of x over minus 1 over x is equal to 0. I will try to show some diagrams, especially when we get to tan of x, to show because the same result is for tan of x over x is also equal to 1 there, but we will wait and get there before we can show that. And so because of that, we can simplify this further. We can take this inside, because sine of x does not contain delta x. We don't need it to be there, so we can take it out and push limit as delta x tends to 0 in next to that bracket, and similarly extend that in here so that it applies only to sine of delta x over x, and we have something of this nature. So dy by dx then is sine of x, limit as delta x tends to 0 of cosine of delta x minus 1 over delta x, and that is plus cosine of x and the next limit there. So as we have already indicated, this limit is 0 while that limit there is 1, and so this first term here is going to disappear, while this term is going to remain cosine of x times 1, which is just cosine of x. And we conclude that the derivative, therefore, that if f of x is sine of x, or if y is sine of x, then dy by dx is going to be cosine of x, which remains there. Let's just confirm that. So that's 0, while the next one there is 1. And so when we simplify that, we get that if y is sine of x, then dy by dx is cosine of x. I hope you are understanding this. Let me know if you're having difficulties, or if you need further clarification, or if you need something else to be added into the video that explains better what we have discussed here. All right, let's go to the next one. Right, now let's take a look at the next one. We want to show that the derivative of f of x is cosine x is something else. I'm not going to do this one, so I want you to try it out, but I've given you a hint with which to try and do this. The results that we found earlier still hold, so you can make use of them to do this. Let's go slightly ahead, so I give you this hint. So if we want to find the derivative of cosine of x, your job is to attempt to show that if y is cosine x, then the derivative is going to be negative sine of x. That's what you're going to show. To do that, you're going to remember or to know the compound angle formula for cosine of a plus b. Why do we call this compound angle? It's because we are putting two angles a and b together and trying to find the cosine of the pair. Okay? The compound angle formula for cosine of a plus b or a minus b is given there. Please notice that when this, in the case of cosine rule, in the case of the compound angle formula for cosine, when this is plus, that one there is minus. And when this is minus, this side is plus. Okay? So keep that in mind. Well, I'm sure you know it, but it's always a good idea to remind students about this. The other thing you need to remember one more time is this results for the limits of sine x over x and cosine of x minus 1 over x. Okay, those still hold. You're going to need that to be able to show that if a function is given by cosine of x, then the derivative or the gradient function is going to be negative sine of x. This is going to be useful for physicists, this together with the previous one, especially when it comes to waves and a few other areas in physics. Okay, now let's go and, so that's your job. Let's go and look at the derivative for tan, which might be a bit confusing to some students. All right, so use the method of first principle to find the derivative of the function f of x is tan of x. If we are going to do this, once again, like I said, always remember to start with that diagram. Okay, it's not really useful anymore, but when you draw it there, it always reminds you of your y2 minus y1 and x2 minus x1 before you proceed to the principle or the equation of the principle. Okay, so here is the diagram. This time we have tan. So for y2 now we have, so for y1 we have tan x because the function is f of x is tan of x. So this is f of x and that is f of x plus delta x. So our f of x is tan x. Our f of x plus delta x is tan of x plus delta x. That's what we have there. Okay, there they are. And so now we can go ahead and use our principle here. We replace f of x plus delta x with tan of x plus delta x, and the same for that. Once again, we know that we need to expand tan of x plus delta x. And to do that, we need the compound angle formula for tan, which we normally derive from the compound angle formulas for sine and cosine. But right now, we'll just put it down. Here is the compound angle for tan, angle formula for tan. For tangent again, if this is, I forgot to put this here, but if this is plus, that is plus, and this is minus. But if this is tan A minus B, so if this was a minus here, if this was a minus there, then this would be a minus, and this would be a plus, okay? So that would be the scenario if this was tan A minus B. But because we are dealing with a sum, we don't really need the negative bit of it. So we'll just proceed. Okay. Next, so let's expand that. So we're going to put that in here, except that our A and B are x and delta x. If we do that, if we substitute that in, that is what we have. Now it might appear, it might look, confusing, but it really isn't. This is a fraction here, and this is tan x. We can put that over 1, and then put the whole thing over one fraction, over one denominator, which is 1 minus tan x, tan of delta x. And if we do that, we end up with this, all right? So if you take the numerator there, this whole numerator, and put it under one denominator, which is 1 minus tan x tan delta x, then this is going to remain as it is up there. But this is 1, this is tan x over 1, and therefore this is going to have to multiply tan x, all right? The same way we add fractions is how you will do this. Or if you like, you can say this as a denominator of 1 minus tan x tan delta x. So you are going to take this and multiply by and divide by this thing so that the denominators are the same, and that allows you to add the numerators and keep them under one denominator. And that is without discussing the delta x at the bottom, okay? Now the delta x at the bottom, so let's just simplify this first. You can see that we have a positive tan x here, and we have a negative tan x right there. So these two must cancel, and that is going to simplify our work a little further. So if we do that, cancel off the positive and negative tan x, we end up with briefly a simplified form of the expression. Well, not exactly simplified, so let me try and do this, just show the result that we get here. So we have tan delta x, and we have tan x tan delta x. So tan delta x is common. Also, I can put this out. I can start with, let me write like this, that a plus b over c, and then if the whole thing is divided by d, I can write this as 1 over d times a plus b over c. So this is still the same thing. So the d can go to the side and become as a fraction, okay? So divide by c divide by d is the same as divide by cd, okay? Another way to see this is to say a plus b. I have students who struggle with these fractions like this. Divide by d, this would be the same as a plus b over c. You can convert the division sign to multiplication. It becomes 1 over d, and you can see that's the same scenario that we have there. And therefore, because we have that, I'll erase this now. Hopefully that helps you see why that delta x can be taken out. And so now I'm going to take the delta x out, this one here, and I'll write here 1 over delta x, okay? It's out of this fraction, this square bracket. And now on the numerator, I'm going to make tan delta x, I'm going to factorize it out. So I'll have tan of delta x into bracket, and this has to be tan delta x, and tan delta x there, this is positive, and that is also positive here. So it's going to be 1 plus tan squared of x, all right? And that's just it, because I've taken delta x out, and everything is over 1 minus, really. Everything becomes minus tan of x, tan of delta x, like that. All right, and then what I can do is to now split them up, because this is tan that, and this is tan and tan there. So I can write this as tan of delta x over delta x, bringing this in, right, over delta x, or better still, yes, and I can put this times 1 plus tan squared of x, everything over 1 minus tan of x. That is not visible, so I'll do this again. So I can put this as 1 plus tan squared of x, and I can divide this by 1 minus tan of x, tan of delta x, like that. And now, all right, and this is under that limit thing, limit, this is under the limit as delta x tends to 0, there, like that. So we can say as that delta x tends to 0, this function here, this expression tan of delta x over delta x, should become 1, and I will show this on a graph, but the proof is also there from topic 3. And we can also say that the limit of this is 0, the limit of tan delta x is 0. So this term here is going to disappear completely, and we will have 1 plus tan squared x over 1, and this is going to be 1. So eventually we are going to be left only with this numerator, which is 1 plus tan squared x. Okay, let me erase that and then write it neatly. Right, so now based on the explanation we've given here, let's see what happens. All right, so when we simplify, remember we had this term here, which becomes just a 1, okay, because the limit as delta x tends to 0 of tan delta x over delta x is the same as the limit as x tends to 0 of sine delta x over delta x, which we looked at earlier. So the limit for sine, this expression for sine is the same as for tangent, and is the same as 1, while the limit of tan of delta x becomes 0. As delta x tends to 0, the tangent of the angle delta x also becomes 0. I think I've shown this on some diagram. Okay, so what we have here is a graph of y equals tan of delta x over delta x. It looks like this. So we can see that as we approach a value of x or delta x, here is the x-axis is delta x. So as delta x approaches 0 from the left, we can see that the value of the function is approaching 1. Similarly, as delta x approaches 0 from the positive side, we can see that the value of the function, which is tan delta x over delta x, tends to 1. So we conclude that the limit of the function tan of delta x over x is always 1. Similarly, we can look at the graph of so that this one here is going to be 1, while the other one there is going to be 0, because you can see this, the graph of y is tan of delta x. As we approach 0, as delta x is approaching 0 from the left-hand side, we can see that the value of the function is approaching 0. Similarly, as we approach 0, as delta x approaches 0 from the right-hand side, the value of the function is also approaching 0. So therefore, the limit of tan of delta x here, this value here, its limit is, as delta x tends to 0, is of course 0, which means this is going to be 1 and this is going to be 0. So we are left with 1 plus tan squared x over 1 there, all right, which becomes our derivative. Okay, we conclude that if a function y is tan of x, then the derivative dy by dx is going to be 1 plus tan squared of x. Well, 1 plus tan squared of x, if you will remember, can be expressed as sec squared of x, because the sec x is the reciprocal of cosine x. All right, so this is one way, therefore, of expressing 1 plus tan squared x. This is another way of rearranging the Pythagorean identity relating sine and cosine. We can write it in terms of tangent and secant. This is also useful in physics when you look at parabolic motion or projectile motion, and where you want to determine the range of the projectile. This becomes important. All right, and that, I think, brings us to the end of that derivation. We have shown that the derivatives of 3 trigonometric functions, sine. Hopefully you will be able to show that the cosine is negative of sine x. And finally, we've looked at the derivative for tangent of x. Like I have said, it is possible to use the ideas that we have used here to extend them to help you find the derivatives of functions, such as you could find the derivative of the function such as y is cosecant of x, y is secant of x, y is cot of x. All this can be determined with the same ideas that we've used before. All right? Thank you very much for that lesson. I hope you are understanding. Let me know what you think. I welcome all good ideas that can come from you. And please remember, if you haven't already done so, to subscribe to the channel and also like the channel, so that when we make new lessons, you will be able to, you'll get the notification. Thank you very much, and I will see you in lesson number 6. In lesson number 6, is now practically just HL students. This is all about using the method of first principle to determine the derivative of a function. Okay, after that we can then go back into the material we have. These formulas, the formulas for the results of the derivatives will usually be there in a formula booklet for most of the exam systems. So we don't really need to ideally know how to derive them, especially if you are an SL student. But if you are a higher level math student, then we expect you also to be able to find the derivatives of any of these functions by method of first principle, including the ones we are going to do in video number 6, which includes things like the derivative of showing that the derivative of a power x, Okay, this is an exponential function. When you find the derivative of this, we find that the derivative, let me use Newton's notation, the derivative is going to be a power x ln of a, and we need to be able to show that. All right, the derivative of a function such as arc tan x, we know the derivative of arc tan x, but we need to be able to show that this becomes 1 over 1 plus x squared. So I'm going back into this stuff. The derivative of log to base a of x, we need to be able to show that this gives us 1 over x ln of a, and so on. So we are going to do this in the next lesson, number 6, and hopefully you will be there. Please, any ideas that you may have for these lessons, I will be waiting to hear from you. Thank you very much.